Okay. So I think this is where we stopped in the last class. I told you that this is false position method. Now, same as bisection method. Only difference is we calculate the root in a different way. We use a different formula to find the new value of the root. And I told you also this is simply an interpolation. Okay. So if you remember, the interpolation formula goes like this. If you want to see, these are the 2 points, XL, F at XL. This is the XY pair. XU, F at XU. Okay, these 2 points. When you want to find a line which goes through these 2 points, you'll write this. If you remember, the equation for line passing through those 2 points, if you remember this thing from, is going to be f of x minus, we can do it either way, f at xl divided by x minus xl is equal to, this is the slope, f at xl minus f at xu divided by xl minus xu. See, this is, I think, okay. So we could use u or l, doesn't matter. So I think it looks like the formula uses u. So I'm using that u. See, this is the equation. If you remember, if you want an equation for line passing through x1, y1, x2, y2. Do you remember how you were doing that? You'll say y minus, either way, x1, x2 doesn't matter. Y minus x1 by x minus x1 equals y1 minus y2 divided by x1 minus x2. Something like that. You remember that, right? That's a straight line equation for a line passing through 2 given points, 1 and 2. Okay. So if you rearrange this, then you'll get the equation to be f of x equals x minus xu times f at xl minus f at xu divided by xl minus xu, that is the slope, plus f at xu. Okay, that is the equation. Now for this straight line, you want to find the x. You know that you want to find x, but if you xr equals to 0, you want to find what is that xr. You want to find out that value of x when x equal to x star, the point that you want to find out, fx is 0. So you substitute this. So 0 equals, this is f xu plus x minus xu. So that's, I'll say as negative xu, xr minus xu. Okay, and then this is the slope, fxl minus fxu divided by xl minus xu. See that this, if you arrange, this is what you get. Okay, so everything else is same as the bisection method. Only little difference is here you're trying to here we are calculating the new root using a different formula. For bisection method, again I'm telling you, for bisection method, the XR equals XL plus XU divided by 2. Okay, this is the only difference between bisection method and postposition method. Everything else looks same. Everything else is essentially the same. Okay, can we go on? Is it clear? Okay, we'll go on. Now, see, I'm telling you, we progressively, once you get the root, once you, this is a bracket, once you have the root in the bracket, okay, you progressively cut the bracket, find which one, continue with this one, cut the bracket, maybe continue with this one, maybe this is where the root is, cut the bracket, maybe this is where the root is, continue this one. That way you go on, go on, go on. But when do you stop? What is the criteria for stopping the iterations? Well, it's up to you. So eventually the width becomes very small, right? If you cut half, cut half, cut half, cut half, usually the width becomes very small. So you can say regarding, when it is enough, when the error is small enough for you to stop the iteration, it's entirely up to you. But generally what we do is we set the criteria for stopping the iterations based on the relative approximate error in the root. Relative approximate error in the root. Do you remember what is the meaning of relative approximate error? If you remember, I told you relative approximate error, which is small e sub a, is best estimate minus approximate value divided by best estimate. Okay, so do you remember what the meaning of best estimate is? What is the best estimate? Anyone? See, in module 2, we learned about the idea of different definitions of error. Right? I told you about absolute error, relative error, true error, approximate error, significant figures, precision, accuracy. What is the best estimate? Anyone?
Close value to correct answer, sir.
Yeah, it is, which is some other estimate than what you have at hand, which is better than what you have. Okay, so in the case of iterations, these iterations proceed like this. Initially, let's say this is iteration number, how many times you have repeated the process, and this is the root you have at that level, xi, xi, let me say xi root at that level, or I'll say ri root at I. So iteration 1, you have first value of the root. Iteration 2, you have different value of root. Iteration 3, you have a different value of root. 4, different value of root. So on and so forth, it goes on, right? Each time, if the method is good, each time the root is getting closer and closer to the true value. It's improving in accuracy. So at any point, for this one, if you want to estimate the error in this one, you can use this as best estimate, because you know that if the method is converging, this one will be a better approximation of the root than this one. So at any level, if you want to find an error, then you take the previous value of the root, new value of the root minus previous value of the root. from the last iteration divided by best estimate, which is the new value of the root, absolute value. Okay, so this for all iterative solutions, wherever there is iteration involved, in such cases, this can be taken as the definition of approximate error. Okay, so that is about approximate error. Then you can decide, when to stop. Now, for example, you can say I'll stop when approximate error is less than 10 power minus 3, and this is your tolerance. No, this is what you're willing to accept in your error, in your solution, and the level of error, approximate error, that you are willing to accept in your solution. Now, this is one typical value. Other ones you can use is 10 power minus 4, 10 power minus 5, or you want to be sophisticated, you can use 5 times 10 power minus 6, something like that, some number. But, don't use things like 1, 2, 10, because this is absurd. You should not be doing that. Some kind of a small number. This tolerance, this is absurd numbers for tolerance. Don't use that. Okay. So this is all the theory I'll cover about the bracketing methods. In the next class, we'll do with non-bracketing or open methods. We'll learn fixed point iteration method, Newton's method, and secant method. That is for the next class. Okay. So here, any questions on the theory part? We'll go to the programming now. Any questions here? See, all we did here is do two methods. And you remember, this is what we did in the morning class. I think in the last class, I used Jupyter Notebook. I showed you how to do the trial and error. Okay. And here I was showing you a more systematic way of doing the trial and error, which is scanning. I asked you that we should rewrite the equation such that it looks f of r equals to 0. This is what the equation should look like. Okay. Then we can do the scanning. Now, and what did we do in the scanning? We started with one value, some value of CD, and then we found what is the value of the function. Which function? Whichever function we got by bringing everything to one side of the equality sign. Okay. The equation generally may look like this. R could be on the right hand side and left hand side also, but bring everything, including constants, bring everything to the left hand side and make the equation look like this. Now this is what you will solve. Okay. For that, you started with some value of CD, and then you're printing CD, and the value for that function you got when you use this value of CD, that you print, and every time you're incrementing the CD value by a small fraction. And then you see what happens. See, since we are trying to find out the value of CD such that this becomes 0. See, we brought everything to one side, right? So what we are trying to get for this expression is 0. So you see, we started with negative number, and it's reducing in magnitude, reducing, and it became here. It got close to 0 here. But important thing is, it is negative here, positive here. In between, we have the root. That is one way of locating the root. Again, it's a systematic way of doing basically a trial and error. You're just plotting the function for a range of values and see which one gives the required function value. And then, I have imported matplotlib and the pyplot, and I have we done the plotting. I created a CD array and the array starts at 0.1, see, 0.1, and it ends at 0.6, and in between we have equispaced points, and the space between two consecutive points is 0.001. 0.001. Okay, so then that is the only array. For rest of them I have used constants. So I used this array and I used np tan hyperbolic function, which gives f array. See, we'll get f as an array also. F will have, so CD has 60 values of coefficient of discharge, and F will also have 60 values for the function, each corresponding to the each being the function value for the corresponding CD in the other array. So we can simply plot that CD array and F array. I plotted it and I also showed grid on it, and I added X label CD and F. Now you can see that here is the root. Okay, that's where it becomes 0. So this is an approximate method. These things you can try. Now what I'll do now is we'll try to solve this equation here. Okay, this is the equation we try to solve. Okay, that's a cubic equation. If if you, when you're doing a problem, if you get an equation like this, and if you're asked to find a solution to that, find the values of x, will you be able to find what those are? Can you tell me? Will you be able to give which values of x? Which values of x will satisfy this equation? Now what I'll do is, first we rewrite the equation as minus 231 equals to 0. Okay, so like I told you, the first thing you should do is bring everything to one side. Then I'll do some plotting. Okay, what I'll do here is I'll start from x equals to np dot a range 1 comma 20 comma 0.01. So I created an x array. Okay, then my function is, I'll create this function. Okay, so x cubed minus 21 times x square plus 131 times x minus 231. Okay, that's my function value. Then I'll say plot these two. Okay, instead of typing all that, because we already have it here, I'll Control C. So I'll say plot x comma f, and x value will say x, and plot grid. That's it. So this will, this is a plotting. We'll approximately know where the roots are, and it's hard to say because it's a very large number. What I'll do is I'll do it to only 12, because the equation is becoming very large. The values are becoming very large. Now you can clearly see. So this is a 0 line. Okay, so there are 3 roots. Of course, it's a cubic, so there are 3 roots. There is a root here. There is a root here, because wherever this line is crossing. Now, once you rewrite the function as this, once you rewrite the function as f of r equal to 0, f of x equal to 0. See, I think I told you here. Once you write the equation like this, then if you plot this function, you should see when this line, when this curve is passing through the x-axis. Wherever it passes through x-axis, that is the root. So if you see this, here's the x-axis, because function equal to 0. Above that, the function value is positive, below that it's negative. So whenever the line crosses this line, this axis line, that's when the root is. So it has three roots, 1, 2, and 3. And in this case, I know exactly what those roots are because, of course, I made up that equation. I made up that equation such that the roots are, this is 3, this is 7, and this is 11. Okay, so it has three roots. Now, again, I'm doing this so that you get a good exercise of the method instead of worrying too much about the complicated equation. The equation itself is very simple, cubic equation. I just multiplied x minus 3 times x minus 7 times x minus 11. I did that simple polynomial multiplication. I came up with this cubic. That's how I made it up. Okay, so we'll try to solve it now using bisection method. Any questions so far? We'll try to find solution to this equation using bisection method. Any questions?
Sir, I have small doubt, sir.
Please.
Sir, yes, sir. We are not import the MATLAB and then we are not import the number now, sir. But directly we will do how it, sir.
I don't think I understood the question. What is your name?
Sir, Maruf, sir.
Maruf. Okay. What is the question again? Can you repeat it again, Maruf?
Sir, yes, sir. You are not import the MATLAB and then also you are not import the number now, sir. Directly you can do. How is it, sir?
No, I'm not doing it directly. See, this is the same notebook I was working on in the morning. So it was, I did all that. See, you don't remember this? I did this in the morning. This is the same notebook. I did not close it. So that session was still on.
Okay, sir. Sir, otherwise we will open the new notebook and then we will also write it now, sir. Hello, sir.
No, I'm trying to understand what you're trying to ask. So
sir,
you want to do it, Maruf?
Sir, okay, sir. Sir, but first of all, sir, we will not first open notebook, sir, and then
Okay.
we will import that math, na, sir.
Yeah, you have to write that import math. You have to do that.
Okay, sir. Okay, sir. Okay.
Okay, I think one of these days I'll have one of Maruf, do you have a laptop?
Yes, sir. Yes, sir.
Are you joining the class from a laptop?
Yes, sir.
Okay. No, one of these days I'll have you share your screen and you do the program yourself. I'll tell you what to do.
Okay, sir. Sir, on tomorrow itself I will also start, sir.
Tomorrow I think there is no classes. Tomorrow is 4th Saturday, right?
Yes, sir. Sir, on Monday yes, sir. I was done one numerical, sir. On nonlinear equation, sir. I was done it, sir, and then I was imported a MATLAB, sir, and then I also a number, sir. That's why I'm also asking to you, sir.
Yeah. No. NumPy and all we have to do. No, this one is a special thing because I did not close the session because I knew that afternoon also there is a class. So I did not have to load it again. It is the same session I'm continuing.
Okay, sir.
If I had closed it and started it again, I will have to load it again.
Okay, sir. Thank you, sir.
Okay. Thank you. Any questions about the problem itself? So we'll solve this equation. So what do we need to solve this equation? What we need here is, first of all, we'll need two initial guesses. See, you looked at this plot, you know that there is a root between 2 and 4. And there is a root between 6 and 8. See, this is a root, this is a root, and that is a root. So 2 and 4. So let us try the one with the 2 and 4. So I'll say XL equals to 2, or I can say 1 also, doesn't matter. And XU equals to 4. So that is my initial bracket, and definitely there is a root in between those two. Okay. Then the first thing I have to do is find the value of function value at lower limit. Okay. So what I'll do here is, I have already plotted this. I'll take this again. This is not a very good way of doing it, but I'll show you better method little later. Control V, and fu equals control B. Okay, so here I have to find it using the lower limit XL value. I'm finding the function value, and using the XU value, I'm finding the function value there. Okay, now I think the second thing is, see what I'm doing. I have taken the initial bracket and the initial thing of the bracket and the second thing of the bracket, upper limit and lower limit of the bracket, and I found the function value. I evaluated the function value for the XL, which is the lower limit of the bracket, and I also evaluated the function for the upper limit of the bracket, which is for the upper no, for the upper limit of the bracket, which is XU. So we have those two. The second thing we have to do is I have to ensure that, how do I check? I can only proceed from here if FL and FU have opposite signs. If they have both signs, then if they both have same sign, then there is no guarantee that the bracket has any root. So that I should not allow it to happen. So what do I do? I have to check whether these two have both sign. These both have same sign. Can you think of a method how you can check whether they both have a same sign or different signs? Can you guys think of any method? Okay, I'll give you a clue. If I'll multiply the function values FL and FU. Okay, if both have the same sign, then what is special about the product? If both of them are positive, then the product will be
Positive.
if both of them are negative, then the product will be
Negative.
if both of them are negative,
Positive.
positive. So we check that. If both of them are, if the product is greater than 0, that means if the product is positive, that means either both of them have a negative sign or both of them have a positive sign. And if that is the case, then we cannot use this bracket. Then if that is the case, then we'll simply print the bracket, the bracket may not contain the root, any root. Okay, so and then there's no point in proceeding. We'll stop here. I think it's called exit and keep kernel equals to 2. So we'll not proceed. We'll ask it to, okay, forget about it. No, so I understood this logic, right? If the product is positive, that means either both of them are positive or both of them are negative. That means that bracket does not have the root. In that case, we cannot proceed with it. Okay, then we do this. Then we have to I put this loop while EA, approximate error, is greater than tolerance. Okay, now I'll give this tolerance. Now we can choose the tolerance, I said, right? So I said my tolerance is 1E minus 5. Okay, that is my tolerance. And EA, because I'm using EA here, I have to define it ahead of time, and here I'll simply make it as 1 for initial time. It doesn't matter, I only want to make sure that it runs for the first time. Okay, so while error is greater than tolerance, what are the different steps in the bisection method? You have to find the root. The root in bisection method, root is simply XL plus XU divided by 2. That is your root. Then you find the function value at the root. See, in the morning I explained, right? You find the function value at the root, then you look at the sign of that. XR. Okay, so you are finding the function value at the root. Now you check. Now, how can you check? Again, use the same logic. We'll check if XL times XR. Now we are checking. You can check with XU also, doesn't matter. But I'm choosing with XL. No, not XL XR, FL FR. FL FR. I'm checking the signs of whether FL and FR have same signs or different signs. If the product is greater than 0, that means both the function value at the lower limit of the previous bracket and the function value at the root, the new root that you calculated, both of them have same value. Okay. Let me go back to the presentation and I'll show you something. Okay. See, I'm generalizing the procedure that I told you in the morning. Okay. So the generalization of the procedure is you have XL, XU. Okay. Now you are finding the midpoint XR. Now, in this bisection method, we are finding the midpoint. False position method, it could be anywhere, but it will be between these two. Okay. Now I'm comparing, FL, FR. I'm comparing FL, FR, whether it is greater than 0. Okay. If it is greater than 0, if it is yes, then if both of them, if the product is greater than 0, that means either both of them are negative or both of them are positive. In that case, this is the bracket first half and second half, let's say. If this is true, which half has the root? FL and FR, the product is greater than 0. If that expression evaluates to be 0, if this is in fact, if this is true, then which half has the root? Anyone? Anyone? No, there's a 50-50 chance that you'll get an answer correct, because there's only two options. Which half has the root? If this, you're checking this, you want to proceed with only one bracket, right? So to make that decision about which bracket to keep and which bracket to lose, you are comparing the sign of this with sign of that. FR times FL or FL times FR. If the product is greater than 0, which half has the root? Anyone?
FR and FU.
FR and FU, that's correct. The second half, if this condition came out to be true, the second half has the root. So for the next time, for the next iteration, you want to continue with this loop. Okay, XL, XU. For the next iteration, you are changing the lower limit to the previous XR. Okay, and this one you'll just neglect it. You just throw it away. It's not needed anymore. Okay, the lower limit you're taking. If this is false, meaning one of them is positive and one of them is negative, in that case, which half has the root? In that case, the first half will have the root. Then what do? You keep the XL and XU you throw away, and this you'll make the new XU is going to be XR. So this is the logic. Okay, if the product has positive sign, if the product is greater than 0, whatever product I'm testing, if that product is greater than 0, then I'll make XR to be the new XL to be the XR, and the old XU stays. If that is less than 0, then I'll keep the XL, throw the XR, old XU, and the XR will become new limit, upper limit for the thing. Okay, so I could have done the same thing, XL, XR, I'm sorry, XR is here, this is XU. Now FR, FU, FL. No, I could have done the similar thing by checking this. I could also check FR and FU. It's okay. This is also fine. If this is true, FR and FU, if it is greater than 0, means this does not have the root. In which case, if this doesn't have the root, you throw this away. XU becomes XR, and XL stays the same. Okay, if this is yes, and if this is no, that means this has the root, so we'll throw away the XL and new XL becomes XR, and XU still stays the same. No, this is no. Okay, again, anyway, it's up to you. You can check these two or you can check these two, but then decide which half has the rule, and just throw away the other part. Okay, so that's what I'll do there in the program. You will see here. Okay, I'm checking it. If that is true, then we don't need the old XL. XL is gone, because if this is true, that means the root is between XR and XU. So I'll make that XR as the new XL. The function value also I'll keep that FL equals FR. Okay. Else, if that is not true, then we keep the old XL, I change the XU. XU will be equal to XR. FU is going to be FR. Okay. So that is bisection method. I have to update the error value. For updation of error value, I'll say EA equals, the thing I told you, absolute of, okay, XR minus XR old divided by XR. That we do, and that's it. That's it. This will this will solve the equation. I'll do one thing here. You know, initially there is no XR 0, so I have to initiate it to something. XR 0. That's XR I'm saying. Okay, XR old equals XL here. No, initially it's okay. So at the end of each iteration, XR old equals XR. Now for the next iteration, I'm saving this one, because next iteration I'll use this one for the error calculation. Okay. So I think before I do
sir.
this, yes.
From EA onwards, explain it, sir.
EA onwards, right?
That
Okay.
term only.
Yeah, sure. I'll show it to you here. Okay. See, yeah. Anyway, see, I think we have to decide when to stop the iterations. Now we have to have a criteria for stopping the iteration. I told you that we will use the approximate error. The new value of the root minus old value of the root divided by the new value of the root. This is the approximate value. This is the approximate error. And whenever this becomes less than tolerance, we'll stop the iteration. That's what we have decided. Okay, that's one approach. So at the end of each iteration, I have to stop and I have to see, okay, this error. I have to compare my new value with the old value. The difference divided by the relative. What is that? Okay. If you want to do this, you have to store the old value, right? For one iteration, you have to store the old value. The previous value you should always know. Only then you can calculate this, right? Is that understood? At any point, you should know what is the root that you found for this iteration, and also what is the root you had for the previous iteration. Okay. Okay. Who was that? Who was asking the question?
Okay, sir.
What is your name?
Rakesh, sir.
Rakesh. Okay,
Yes.
Rakesh, I'll make it clear for you. 1 second. Okay. Now, so say this is the first iteration. Let's say you're doing the first iteration. When you do the first iteration, there is no such thing as the previous iteration. Okay. So that's why before the loop, I have, this is kind of arbitrary. I had two initial guesses for the root. Okay. Out of those two, I have taken one as my old value. Okay. Now, when I find the new one, I'll compare that new one with the old one, and I'm finding what is the percentage error or what is the relative error. I'm storing it here. Now, the last step in the iteration is for the next time, whatever this root I have now in this iteration, for the next iteration it is old one, right? So I have to save it. I'm saving it I'm overwriting. So previously, for example, okay, see in that example, iteration and root for that iteration. Iteration 0, initial one. No, I'm taking the lower limit, which I think is 1 there. Okay. See, I'm doing the iteration if you in that for xl equals to 1 and xu equals to 4. Okay. This is my initial bracket. So initially the root is 1. After I do the iteration 1, the root is going to be 3. Now I'll compare these two. So initially I call this one XR0 and this is XR. At the end of the first iteration, what I'm doing is I'm changing this to, I'm calling this as XR0 at the end of the first iteration. And the next iteration when I do, this is 2.5 actually. In the next iteration when I do, it will calculate the average between 2.5 and 4. I don't know, 3.25 or something. Then then this is XR. It will compare between these two. Next iteration, at the end of the second iteration, I'll make this one as XR old. The third iteration, the comparison will be between those two. See, the thing I'm doing there is the last thing I'm doing in the iteration. At the end of the iteration, I'm storing the root and that iteration as XR0. At the beginning, immediately when the loop comes here, this XR gets overwritten, but I have stored the old value, which I'll use in the calculation of the error at the end. Is that understood? I'll print it here. I'll print here. For example, let me say I want to print the iteration number also. I'll say iteration number. So I have to keep a count of that. So what I'll do is I'll say iteration number equal to 0. At the beginning of each iteration, I'll add it. Iteration number plus equal to 1. And I think I told you, right, this is augmented assignment, which means this means iteration number equals to iteration number plus 1. That's what the augmented assignment means. I'm doing that so that I can print. I'm trying to get an output where I'll print a table, iteration number, comma, XR, comma, X. I know. I think this will make it clear for you. XR old, comma, error. Okay, I think I'll print. XL, comma, XU, comma. Okay, and I think this will not look good if I don't do the rounding. So let me do the rounding to 4 digits maybe. Because I'm printing like a table, I wanted to look it. I wanted it to look clean. Yeah, I'm rounding off the digits because otherwise it look. I'll show you what I mean. Okay. See, when I print to the slide, when you get all these multiple digits, it's difficult to see. So I'm asking it to round it off to the 4 digits, all those things. So for each iteration, it will print the iteration number. What was the lower limit? What was the upper limit for that iteration? What is the root found in that iteration? What is the root in the previous iteration? And what is the error? Actually, I'll do this here immediately because after that it's changing the values. Okay. 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 See, this is all. This is the method. So I'll run it. Obviously, there's an error. What does it say? Error is not defined. Okay, not error. It's EA. Okay. Now we'll print it. Now here's the thing. It took 16 iterations, but it found the tree root. You see, this is the upper limit. This is the lower limit. X1, 4, and the root is 2.5, and old root is 1, and the error is 0.6. In the next iteration, second iteration, you see the lower limit has changed. We changed the lower limit to 2.5, upper limit is still 4, and the new root is 3.25, and the old root, see, it was old root, right? That 2.5 is here, and the difference, the relative error is 0.2308. In the third iteration, see, the lower limit did not change, but the upper limit changed. The upper limit was 3 before, but now it became 3.25, the root from the previous iteration. And the new root is 2.875, and the previous root, old root, see, it was there, 3.25. Now it is here, and the error is that. So likewise, the error reduced, and eventually it found out, we got the value, the error value as 3. No, the root as 3, which is correct root, right? I told you that the root was 3. 3 was one of the roots here. Any questions here? one major improvement, a very interesting improvement we can and we should make to this one is we should never write the function here directly, because if you want this to solve a different function now, okay, then you have to change this line, this line, this line, everything. Instead of that, now what you should do is we can define a function to evaluate that. I think you remember functions, right? Function of x, and then you can say return. See, instead of writing the entire function wherever we have to evaluate the function value, 3 places, we are typing the whole function. Instead of that, if you move that here, so here, since I'm calling it x, I'll simply call it as x here. For the equation that I have, for the expression that I have written a separate function. I'm calling it f. Okay. Now I think what we do here is I don't have to write all this. I simply have to write f of xl. And similarly here, I don't have to write the entire function here. I'll simply say f of xu. If you remember the Python, now whenever it comes here, this is a function call, it goes there and it evaluates using this xl value, it will evaluate the function. Here it using the xu value, it will evaluate the same function. Okay, doing it that way, again here. And here it's going to be f of xr. That's a that's a very important thing we have to do. If you use it as a function, if the answer is same, it doesn't change anything. But the benefit is, if you want to solve a different equation, let's say you want to solve that. If you want to solve a different equation, all you have to do is change this function. The main program can stay the same. Now what I'll do is I'll use this one. So if I want to same program, I will use to solve that other problem, the bungee jumper problem. Only thing is, instead of CD, because the function, this is my x now, instead of CD, I'll make it x. Okay. Okay, same, this program is same. But now when I say function, it is instead of getting the polynomial value, it is getting this bungee jumper problem. So accordingly, I'll change this to be 0.1 because that one has the root. Okay, that's all. Now this will solve the bungee jumper problem. It did not. Maybe I did not run this one. No, there's a problem. I didn't say written here. That's why it sent a none. Python is a serious thing. It's time up. Anyway, you see the same, the same formula. I only changed the function. It is solving a different problem. Okay. If I comment this out, no, I thought there is a method to. Okay. Anyway, I'll delete it. Doesn't matter. Okay. So if I'm using this as a function, if I'm returning this, I run this. It is solving the polynomial problem. Okay. Now if I change this function, I run this, this is solving the bungee jumper problem, 0.4231. That's the bungee jumper problem in 20 iterations. Okay, anyway, I don't want to keep you. Any questions quickly? Okay, I'll stop sharing and also stop recording.